No.
Talking away, though I don't know what to say.
That's not aha. Is it? Is that Weezer? You are welcome. So this is the periodic table, and let's just be real here. This has got to be the weirdest table you've ever seen. I mean, if you look at it, why not pick a rectangle or a square or just something that has a consistent number of columns and rows? I mean, we literally have blanks everywhere on this table. I picked one that was colored so we could talk about all the families and everything on there. But truthfully, when you look at this, you should think about this and say, this is the worst example of a table I've ever seen. I mean, nothing seems to be in order whatsoever. And the fact of the matter is, it's perfectly set up to watch almost every trend as we kind of walk our way through. So let's start with the easiest one. Okay, so when I'm first introducing metals and nonmetals, I usually start this off at the lab. But since we're not in class, and even if we were, we couldn't share equipment, let's just do the lab together to make some sense out of this. All right, so let's read this out here and figure out. Also, don't pay attention to the fact it says honors on here. It's fine. We'll work through it together. So, as we begin our exploration of the periodic table, one of the most recognizable patterns or trends that can be observed is the distribution of metals, nonmetals, and semimetals, or as we're going to refer to them, metalloids. This pattern is extremely useful in determining whether an atom will form a cation, a positively charged ion, or an anion, a negatively charged ion, and whether the bond between two atoms is ionic, covalent, or metallic, something we'll investigate more in our next unit. After reading pages 164 to 166 in your textbook, okay, you don't even have a textbook. You do? Excellent. Read pages 164 to 166 in your textbook. Go ahead and pause the video now while you read those. Now that you're back, you're going to create a Venn diagram to show some of the characteristics or properties of each of these. Use the example below to get started. Okay. Let's just talk. So, there's a couple of different properties we're going to look at. Let's skip to the next page of this so you can kind of see what I'm talking about. This lab, you're going to identify 5 unknown substances in order to classify them as metals, nonmetals, or metalloids. The physical properties you'll consider are luster. Luster. It's how shiny it is. Oh, okay. So if it's lustrous, it's extremely shiny. We'll also look at its form, if it's powder, crystalline, flaky, or I don't know, something in between, and whether it's malleable or bendable. So we're going to smack it with a hammer and see what happens. Or brittle, smack with the hammer and it doesn't go well. And then also its electrical conductivity. Finally, you're going to examine one chemical property called reactivity. For this property, you'll examine how reactive your unknown substances are with hydrochloric acid. This is a great lab. It's kind of a middle school lab, but it's still a great lab because at the end of the lab, you get to actually jump a bunch of acid on top of things and see if it makes some cool bubbles. So, normally what we do is we talk about, okay, what are we looking for? So we have to kind of classify these properties into whether they're metals or nonmetals. And so if we do that, we think about, okay, let's think shiny. Metals or nonmetals? What do we think? This one should not be hard. So when we talk about something being lustrous or shiny, that will fall into the metal category. And then the opposite of lustrous or shiny is what we usually refer to as dull. So far, so easy. Okay, physical properties of whether or not it's powder, crystalline, or flaky, that's actually a little tricky because you can change almost anything into a powder or a crystal depending if it's brittle or not and sort of how you work with it. So I'm going to just kind of leave it as if we're in class together, we could talk more about it. Right now, it's not going to help us identify this. Malleable or bendable? So malleable means it has the ability to be smacked with something very hard and actually flattened. Sometimes we talk about it as being ductile, and ductile means you can sort of twist and pull or stretch these things. So if you think, for example, your, part of your car, if you were to smack it with a hammer, don't do that, but you could imagine, you could make a dent. Things that make a dent are malleable. Versus on the other hand, if you smack your phone, you're not going to dent your phone, you're going to shatter it. So that is an example of something that's brittle. Metals tend to be very malleable. Nonmetals, brittle, which are going to be the opposite there. And the last one we consider is conductivity. So this isn't going to be a surprise. Every wire or thing you've ever plugged in is made of metal. Metals are extremely conductive. They're conductive of heat. They're also conductive of electricity. Some are better than others. Nonmetals, not so much. So as we start to look at it, don't get this confused with solids and gases. It's metal and nonmetal. Any one of these can be solid, liquids, or gases depending on their temperature. Oh, one last thing I forgot. The one that's already filled in for you. Metals can react with acid. Nonmetals tend not to. Now that's not perfect, but it's good enough for us. So we're going to use this information to figure out the pre-lab questions. So you observe that a substance is shiny, bends without breaking, and is electrically conductive. Based on your observations, would you classify this as a metal or a nonmetal? So it's shiny, okay, it's metal, bends without breaking, metal, and electrically conductive. I think I'm going to classify this one as a metal. Doesn't even ask me why. We're just checking off the little observations here. Perfect. In the real world, not all substances are found in excellent condition. Wah, wah. We are accustomed to working with. Therefore, not all physical characteristics are as reliable as others. One example is a substance's color. Why do you think color of a substance is not a very reliable characteristic and should not be the only characteristic used to identify a substance? So I got a couple ideas here. If it's rusty, it's going to look a different color. It's also going to change its properties because that's actually a chemical reaction. We can paint things, we can color things, we can add waxes to them like a crayon. Color is really easy to mess with. And color usually is what throws kids off a lot because somewhere in middle school or even in biology class, you learn that a color change is an indication of a chemical change, which sometimes it is, but not always. Usually, what I like to think of it is a brand new color shows up. So you have two colorless solutions mix and turn yellow. That's a really obvious color change. But if you go from dark red to light red, I mean, you might have just diluted something. That's not a color change as far as we're concerned. So normally in class, we'd talk about, okay, let's look at the luster. Let's look at this. We'll fill out all this stuff. What are the four signs of a chemical reaction? Don't get too nitty gritty here. Usually, if we talk in middle school, the four we always talk about is the production of a gas, um, the release of heat or pull in of heat, the formation of a precipitate, and then oftentimes we do mention color change because color change does indicatively mean we're making a brand new substance. For our purposes, it's not a big deal because we're going to just look at the reaction of acid as we kind of go through this. So, this is where normally we'd make a data table, we'd come in the next day and we'd run this whole lab through. So we would take this and we'd find out we have a substance A, B, C, D, and E. Now, what I've provided for you here is actually enough information for you to figure out what the substance is using isotopes, which is from last unit. We also need to sort of make a data table so we can see what would have happened, because I need to give you some actual data to sort of analyze this. So I'm going to do that right now. And the way I'm going to do it is directly on this sheet. So if I go ahead and I'm just going to do a break page. So insert, page break. I'm going to go ahead and make a data table. So let's insert a table. And I don't even know how many, let's just do 3. I don't know. How many do I need? Well, it says I have 5 substances. So, and I'm testing, what am I testing? Luster, form, malleability. So 1, 2, 3, 4, 5 tests. By 5, I need some more columns. Okay. Insert column to the right. Insert column to the right. Insert column to. So I got 5 columns plus 1 extra for my substances down there. All right. So substance. This font is weird. Let's go ahead and just make this not Comic Sans because we'll lose our no, not Times Roman. Let's just go calorie. That looks good. Substance. Okay. 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 What am I testing again? What am I testing? All right. So luster, luster, form, malleability, malleability. conductivity, and then reactivity. So I have substance A, B, C, D, and F. No, E. And so what I would normally do this with you guys is I'd have these substances out in little beakers and we'd take a look. And if we went through all of this and saw kind of what these substances were, well, you can kind of already tell. Because if you remember your isotope stuff, the one that's the most abundant is really close to that average mass. So, for example, substance A is really close to having a mass of 32, because 95% of substance A is mass 32. The other ones are 33, 34, and 36, but they're kind of small amounts. So it's 32 points something. Here's where you could look on your periodic table and find out what it is. Substance B is really close to a mass of 12. Substance C is really close to a mass of 24. Substance D is all over the place, but it's probably somewhere in between 64 and 66. And then substance E is really close to 28. So if we keep all that in mind, now I can give you some information about this. So the luster of substance A ends up being very dull. Its form is kind of flaky. It is brittle, not conductive, and it does not react with acid. In fact, it stinks. It smells terrible. Substance D is dull. It's a powder. It's brittle. And the way we'd know that is because it's already a powder. If you can make something a powder, it's brittle if you're smacking it with a hammer and powderizing it, if you will. Now, what's weird is sometimes substance B is conductive, but for the most part, it's not supposed to be. And then it shouldn't really react with acid either. Substance C, it's kind of shiny, sorta. It actually is kind of like a glob. Globular is a word we'll use. It is actually malleable, so I'll just say malleable. It is conductive, and it does react with acid. Substance D, this one's actually a lot shinier because it's just usually a nicer form of what I have. This is almost like a spherical. It is malleable. It is conductive, and it actually kind of reacts with acid. Not great, because our substances aren't that perfect. And the last one's really strange, because this one ends up being shiny. It's flaky, which we found out, doesn't really help us, but it's brittle. Okay? It's conductive, but it doesn't react with acid. And so then from these substances, we can now use the information to try and figure out what these are. Okay, so I'm going to highlight a few things here and try to identify, okay, well, what was metal, what was non-metal, and then see if we can notice any trends on these here. So I'm going to highlight in green anything that was going to be a non-metal characteristic. Now, if we went back and saw this, our non-metal characteristics, these things that were dull, they were brittle, they did not conduct, and they did not react with acid. Okay, so dull, brittle, not conductive, doesn't react with acid. And then obviously the other way would be shiny, malleable, does react with acid. Okay, so I'm going to highlight those red just so we can kind of see them. Unless you're colorblind, then I guess you might not be able to see this. This was not good planning by me. I apologize in advance. Okay, so now we start to see is, hey, substance A and B pretty much fall almost perfectly in line as being nonmetals. Substance C and D are metals, and then, hey, look, half and half. I wonder if that's a metalloid. So now let's figure out what the substances actually are. So with this information, if we know substance A is pretty much 32, if you look up on your periodic table, you'll find out that substance A is actually sulfur. And it is like this yellowish sort of powder, and it stinks when you hit it. It smells awful, actually. Substance B with a mass of almost 12 is actually carbon. And then substance, this is confusing with the letters. C with a mass almost of 24 is magnesium, which you may have seen before. And usually we have little magnesium strips that are actually a lot of fun to sort of throw inside the acid. Substance D with a mass almost of 64, 65-ish is zinc. And then the last one, substance E, is actually one of the coolest ones to see because you don't see it a lot. Is silicon. Not silicone, silicon. Silicon is actually what's used in microchips. Now, what we just found out is trying to figure out, okay, based off your periodic table, where are we going to see these metals and nonmetals and metalloids? And so if we start to identify it based off of kind of this picture here, I'm going to try and highlight it using, I don't know, one of these things. So I'm going to highlight this periodic table and color on it a little bit. So we saw that sulfur was used and carbon were used. Those were nonmetals. And then we had what? Zinc. We had magnesium. And then silicon was a weird one. Silicon was kind of like, okay. And so then we try to make up this idea of like, generally speaking, where do we tend to see most of the metals? And on our periodic table, when we're doing this, our metals tend to be over on the left side. Now, is that a coincidence or is that the way we designed it? That's kind of where we're going. And then our metal or our nonmetals tend to be over on the right side. Now something really weird shows up in the middle where they mix. And so we draw this thing called a staircase. And this staircase sort of separates what's known as the metalloids. Now you'll notice some things on here like aluminum, it's not truly a metalloid. Our true metalloids are going to be things like germanium, arsenic, antimony, tellurium, and then it gets kind of radioactive, so I don't know if you want to go there, but I guess sure, polonium and astatine, why not? These are basically existing for less than a couple seconds in time, so don't worry about it. So our big metalloids, as we look at it, silicon, germanium, arsenic, antimony, and tellurium. Most of the time I pick silicon or germanium when I'm talking to you guys about it, which then tells us like the rest of this is sort of non-metal stuff. Now you got to be careful because there's one non-metal that's out of place, hydrogen. And it's over here for another reason. And we're going to get into what that reason actually means. But let's double check these questions. Okay, so now we have a generalized idea of where these things are located. We don't know exactly why we put them there, but they're over there to look at for the most part. So then if we can predict what are these things going to be? So potassium's over here on the left. So you guessed it, potassium is a metal. Okay. Chlorine is over here on the right. Chlorine's a nonmetal. Silver's in the middle here, but you know what silver is. Silver's definitely a metal. And then germanium is sitting right there next to silicon. And so I would always have this staircase drawn in for you guys so you could see it better, but germanium is one of our metalloids. So that kind of takes us through the first trend on our periodic table, metals, nonmetals, and metalloids. So from our little investigation, we see the periodic table is sort of arranged with the metals on the left and the nonmetals on the right. Now, we don't know exactly why just yet that it's been done that way, but we know that the two have very, very distinctive properties, where metals tend to be sort of shiny in terms of luster, malleable, conductive, reacting with acid. Nonmetals tend to be the opposite. So they're relatively dull, non-reactive with acid, not very conductive, and also very brittle. Now, there's one real weird one on there, and that's hydrogen sitting way over on the left with the metals. So there's got to be something else that's happening there. And for that, we have to truly discuss what a family means. Okay, so back to that original periodic table we saw at the very beginning, the one that had all the families on it. I like this one the best because really it's showing the entirety of the periodic table in terms of families. And you'll find that some of these families are kind of weird. They sort of go in different directions. So if you kind of follow the first column, which is the vertical section up and down, you go hydrogen all the way down to lithium, sodium, potassium, rubidium, cesium, francium. That looks like a family except for the very first one on top, hydrogen. Hydrogen is such an odd element, no pun intended there. It really doesn't belong to any family. It's sort of on its own. So we tend to just call it a non-metal. But below that column, lithium through francium tend to have very, very similar properties. Those are what are known as the alkali metals. Now, adjacent or next to the alkali metals are called the alkaline earth metals. These elements also have very similar properties. Now, remember, the entire purpose of a periodic table to even have a family is to kind of group the elements that have similar properties together. Now, our alkali metals and alkaline earth metals are very close in name and also very close together on the periodic table. Here's the nice thing about it: it says the word metal in their name. So if you're ever trying to figure out if they're metals or nonmetals, it literally says metals. So that one makes it a little bit easier for us to look at. The third family we tend to look at doesn't really go in a column, it's more of a big chunk in the middle of the periodic table. So we tend to call these ones the transition metals. They're sort of transitioning across the periodic table. And so that would start at element 21 or scandium and run all the way over to zinc, and then all the way down to mercury, or if you want to go to the elements that only exist for a small period of time, I don't know what that is, californium, mercurium, or something else at 1 or 112. It's an element that was recently discovered in my lifetime, so let's just not even consider too much of that on there. I'm going to pretty much go down to mercury. These metals are the ones you usually think of when we talk of metals. So things like copper, zinc, silver, maybe you've seen cobalt, iron for sure. And those are transitioning across the periodic table. Now, if you look really closely in there, you'll see it jumps from element 57 to element 72, and it's orange. And then underneath it, it jumps from 89 to like 104. There's actually an entire set of row or two rows that are basically taken out of the periodic table so that we can sort of condense it into one spot. Now, those two rows are full of families, but they actually run as a row from left to right. Lanthanides are the ones that are going to be the top, starting with lanthanum. Actinides would start with actinium. Those are not something we talk about in standard chemistry. Now, if you do care, those are the ones that sometimes are just called rare earth metals. They're very strange elements. They tend to have some very unique properties. For example, neodymium element number 60 ends up making really strong, like almost super magnets. If you go down to actinides, americium, plutonium, and uranium are used for nuclear chemistry. So there's a bunch of strange elements down there as we sort of transition across. Now, where this gets a little weird is we have this gray section. And the gray section doesn't really belong either anywhere else. It's getting close to that staircase of metalloids. Aluminum, gallium, indium, tin, thallium, lead, bismuth, and then if you want to count the one that doesn't really, whatever. These are other metals. Sometimes they call them post transition metals. But for us, we're just going to call them metals, and it's fine. Even if you call those transitional metals, I'd be like, sure, fine. But it does really stop with the row of zinc, cadmium, and mercury, in case you're curious. And then in columns 13, 14, 15, and 16, if you look vertically, they're not actually a family. Now, if you run down that column, it doesn't make any sense. It starts like with a nonmetal, goes to a metalloid, and then to a metal. But that's not a functional family as far as chemistry is concerned. So we sort of skip those and go all the way to the 17th column, and we mark that one in red. That's called the halogens. Now, this is the one you will always forget. It is the one that shows up constantly in chemistry because they're so reactive. They're the most reactive nonmetals. So, from chlorine, bromine, iodine, and astatine, those are the ones we'll see a lot when we start into chemical bonding. And just to the right of them are what we call the noble gases. These are the non reactive gases. So the concept of nobility comes back to way into the early industrial revolution, the time of monarchies across, industrialized Europe. The monarchs, or the nobles, didn't do much. They sort of were just there. And these are those elements that do the same. They're inert or non-reactive. They are kind of just the end. And so as we kind of go through the periodic table, you see that as every new row starts, we sort of rejoin with a new element from the family that existed in the row before. And we kind of go left to right across there and sort of taking little pieces out. Now that's just the basics, because when we start getting into more detail with this, you'll see there's even more to it than just these families. But that's an overview that should give you enough to sort of look at it.